We did a bunch of these. All right, so we did problem number 1 with the baseball that was thrown downward, all the way through the second part. The rack that was thrown upward. We did. All right, it's part 3. Sorry, problem 3. We have a ball that was punted vertically, and it has a hang time of 3.8 seconds. What was its initial velocity? Make a well-labeled diagram of the situation, make a list of given quantities and quantities defined, label with units, and appropriate algebraic signs. So the axes on the graph that I drew here are height on the y-axis, and then along the x-axis we have time. So that's not horizontal distance. So don't think about it in terms of the object got punted across the field. This is just telling us the motion of the object through time. The way the object actually went was straight up and then straight down, right? It's punted vertically. That's what we were told. So we've got this chart here, and we know some things about it. We know that our acceleration is always minus 10 meters per second squared because our ball was punted on Earth somewhere. We know that at this peak here, at the highest point that our ball reached, that at that time, the velocity was 0 meters per second. We also know that the total time that it was in the air was 3.8 seconds, and that that point where our velocity equals 0 happened at 1.9 seconds. So this thing says make a list of given quantities and quantities to find. I have a tendency to put them on my picture just so that I can keep track of where all that information is, because it kind of matters. You know, what time are we talking about and what are we looking at here? So we're asked to find the initial velocity. So the initial velocity is going to be the velocity right at this point where that ball was released. That's what we really want to know. So the way that I would approach this problem is I would just consider the first half of this motion, because that's where we know information. That's where we can say how much time has passed. We can say it's been 1.9 seconds. We know that our velocity at that point is 0. And we know that our acceleration is minus 10, which means we know 3 things. And we said that when we know 3 things, we can solve for the other one. So if we just consider that first half, this part of the motion, we've got our time. We've got 1.9 seconds for our velocity, and this would be our final velocity then, is 0 meters per second. We're trying to find that initial velocity, and we know that acceleration is minus 10 meters per second squared. So if we refer back to our equations, do we have enough information? We got final velocity, initial velocity, acceleration, and time. So we're just going to use this first equation from our equation sheet. Oops, that's just a plus. Acceleration times time. We're going to solve for initial velocity. Our final velocity here is 0 meters per second. That's equal to our initial velocity plus our minus 10 meters per second squared times time, which is 1.9 seconds. So if I just fill in the values that I know and then solve for initial velocity, what I find is that my initial velocity is 19 meters per second. We find that it's a positive value, and that makes sense because our object is moving upward, and we kept our acceleration as minus 10 meters per second because we know that acceleration is downward. It's opposite the direction that we kick the ball up in the air. Can you imagine if we lived in a place where acceleration was upward? We wouldn't be stuck on Earth anymore. That would be a pretty crazy thing. All right, so that's the thing that we're trying to solve. And problem number 3, does anybody have any questions about that one? Nope. Okay. Problem number 4, a rock is thrown straight up with an initial speed of 22 meters per second. How long will the ball be in the air before it returns to the thrower? So what we're trying to find here is time. Graph the vertical position, velocity, and acceleration on the rock on the axes provided. Make a well-labeled diagram of the situation. So I'm going to draw a diagram of the situation. There's the ground, and my rock gets thrown up with a velocity of 22 meters per second, and it's going to go straight up in the air, and then it's going to come straight down. So we know that when it's released, it has a velocity of 22 meters per second. And just like we did before, we know that up at this point, the velocity is going to equal 0 meters per second. And we know that the acceleration is minus 10 meters per second squared. So the 3 things that we know. Now, if we solve for time for this, what we're going to end up with is the time at the peak. And so to find out how long until it returns the throw, we'll have to double that because it's only the half time. I'm going to go ahead and solve that. Initial velocity is 22 meters per second. I'm trying to, let's see, final velocity is 0 meters per second. Our acceleration is minus 10 meters per second squared. Time is what we're trying to find. So our final velocity equals the initial velocity plus acceleration times time. Our final velocity was 2 meters per second. Initial is 22 meters per second. Okay, so then to solve for time, first thing we're going to do is subtract 22 from both sides. So minus 22 meters per second equals minus 10 meters per second squared times time. And then if I divide both sides by minus 10, I find that my time is 2.2 seconds. But keep in mind, that's my time to get up to the top. So the time to get back down to the bottom here is going to be 2 times that. It's going to be 4.4 meters per second. Oh, sorry, just 4.4 seconds. I just got carried away with my units there. 4.4 seconds. Then when I'm drawing my my charts over here, I don't know how high my object went. I didn't bother to calculate it, but I do know how long it was in the air. I know that when my object reached the peak that it was 2.2 seconds, so I'm going to put that on here. And I know when it came back down to the bottom that it was at 4.4 seconds. So I can at least include that data on my graphs, right? So my object, let's see how I can draw this. I don't know, circles for me, I can always draw better if I kind of like turn my hand a little bit. Still not great, but I'm trying to draw a symmetrical circle, a semicircle. So my object went up and then came back down. For velocity, do you guys remember when we talked about these earlier in the year and we said that our velocity was the slope of our position versus time graph? Because our velocity is going to be our change in time divided by, our change in position divided by change in time. And that's how we could get that is by looking at the slope of that graph. So if I look at the slopes across here, I can see that they change and that they go from a positive value to 0 to a negative value, and they go to 0 at that 2.2 position. So I know that at 2.2 seconds, I'm going to have 0 velocity. And I know that my, since I have a symmetrical shape here, that the magnitude of my velocity at the start is going to be the same as the magnitude at the end, but they'll have opposite signs. We know that it starts with 22. So I know if I put something up here, that this is 22 meters per second. And then I'm going to go down to minus 22 meters per second. So there we go. There's my velocity line. And I know that my acceleration is minus 10 meters per second. The other thing that I know is that acceleration is equal to my change in velocity divided by my change in time, which is a variation of the equation that we actually use to solve this problem. But if we look at the slope here, we can see that it's a constant negative slope, which is consistent with our understanding that that should be minus 10 meters per second squared. My line's actually going to be a straight line across here, and it's going to be at minus 10 meters per second squared. You guys have any questions about number 4? No? Okay. So then in part B, it says draw a velocity and an acceleration motion map for the trip. So this is actually a little tricky if we actually want to be quantitative about it, because we know that the turnaround point is at 2.2 and it comes back at 4.4, which means it's a little bit more than 4 seconds, which just isn't that many dots, right? I like to draw these when objects are thrown straight up in the air. I actually like to draw vertical motion maps. It's just my preference. But you guys can draw horizontal ones, and it's the same thing. It's just an orientation difference. So if I were going to draw this guy, I have 0 meters down here. I don't know how high I went, but I think it's probably, see, we probably went 22 meters in the first second, probably 12 in the second. It's probably 30 meters, but you know, it's fine because this is just relative. So if we start at time equals 0, we're going to be over here. After 1 second, we're going to go most of the way. Our object turns around at 2.2 seconds. So if I put t equals 2, we actually have an object that's kind of turning around just past that. So I'm just going to draw this little line here with my pencil, just so that we can kind of get a sense of what the path here is. Just so you guys can see what I mean by that. So the object would actually go up a little bit further. And then that means that, let's see, when the 3rd second passes, we're probably here, 4th is here, and then we strike the ground again at 4.4 seconds. When we put our arrows in for our velocity motion map, make these big and obvious, we need to draw them halfway between the 2 dots, just like we did before. This one's tricky. For an acceleration motion map, I'm going to have dots in the same locations. All right, if I wanted to try to clarify this with pencil, I could do that. And with acceleration, we know that through the entire motion, the acceleration is constant. It does not change. It's always minus 10 meters per second. So on our chart here, our arrows should always be downward because it's negative, and they should always be the same length because it's the same. So what that tells us is that the entire time this thing is moving, the acceleration is going to be towards the ground. And what that means is that when we have a positive velocity, the acceleration is going to reduce that velocity until it's 0. And then once our velocity is 0, it's going to continue to reduce the velocity until it's a greater negative number. You guys have any questions about the motion map? You guys remember motion maps? Okay. Number 5. Guys, this is a very dangerous activity to do, by the way, even if it's in the name of physics. Throwing things off bridges. I used to ride my bike downtown. You guys ever ride on the bike path? And like this one time I was riding by myself and kids started throwing rocks at me from a bridge. And that was a little alarming. It's like, I don't feel safe doing this anymore. My dad would always be like, why don't you ride your bike? I was like, you want to go with me? It's like, he did most of the time. Okay. He actually was more into biking than I was. All right, a student throws a baseball of a 120-meter high bridge with an initial downward speed of 10 meters per second. How long does it take to hit the ground? How fast is it going? And then a different problem. So the first thing I'm going to do here is draw a picture. So I'm going to draw my bridge. Here's my bridge. I'm just making it a little bit fancy. And here's a kid on the bridge. And the kid throws a baseball with a downward speed. So my initial velocity there is going to be 10 meters per second. It's downward, so I'm going to make it minus 10 meters per second. Anybody make these all positive values? Where'd you guys go with negative values? You made them positive?
I did negative.
You did negative? Okay. So our baseball is going to go downward with a negative velocity. We know that the acceleration is minus 10 meters per second squared. And we know that it's going to travel downward 120 meters. And so that total downward distance, let's just write this in here. Our total downward distance is going to be minus 120 meters. So all of those are negative. Since they have all the same sign, if you wanted to, you could choose to make them all positive. If you don't like dealing with negative numbers in equations. But either way works. It asks us how long does it take for the ball to hit the ground. So what we need to solve for here is our change in time. How much time passes before it hits the ground? So if we've got time, initial velocity, acceleration, and change in position, I put an X there. Let's put a Y there, because that's consistent with our paper on the front. So let's see, velocity, final, initial. This one doesn't even have distance. If we wanted to use this middle one, displacement, initial velocity, time, and acceleration, this is the one I think we're going to need to use. So our vertical displacement is equal to our initial velocity times time plus 1/2 times acceleration times time squared. And we are going to solve for time. So our displacement is minus 120 meters, which is equal to minus 10 meters per second times time plus 1/2 times minus 10 meters per second squared times time squared. I'm feeling good about this one. All right, so I've got minus 120 equals minus 10t plus minus 5t squared. All right, we've got a quadratic that we have to solve for here. You guys like quadratics? I actually kind of do. My daughter's been doing these in her math class, and it's kind of fun. We race on them notes because they're still all easy. Okay, so I'm going to rearrange some things here. I'm going to add 120 to both sides. So then I'll have 0 equals my minus 5t squared minus 10t plus 120. And since I'm solving for t, next thing I'm going to do is factor out the negative 5 so that I have t squared by itself. Minus 24. And now what I can do is divide both sides by minus 5 so that it removes it from that equation. So then I have 0 equals t squared plus 2t minus 24. The way that I think about these is I need two factors for 24 that have a difference of 2. The way that I usually think about these in my head is I start with a little chart. I don't know what teacher taught me this, but it works. If I say, okay, I can do 1 times 24, 2 times 12, 3 times 8, 4 times 6, and then 5 is the number left, and 5 times 5 is 25. So I know that those are my factors. And if I take a look at these, the one that has a difference of 2 is 4 and 6. And so if I use 4 and 6, I can make the 6 positive and the 4 negative and be able to get this plus 2. So say t plus 6 times t minus 4 equals 0. Which means that one of two things has to be true. Either t plus 6 equals 0 and time is equal to minus 6, or t minus 4 is 0 and t is equal to 4. And remember, these are figuring out seconds. So we're either going 4 seconds in the future or 6 seconds into the past. What do you guys think? Should pick one? Which one did you guys like? You guys are all like very quietly like. Okay, so the one that you should pick is 4 seconds. Why are there two solutions there? What's up with the minus 6? Where's it come from? Any thoughts? Do you guys ever wonder that? Where the other number come from and what does it mean? I think it's kind of interesting. So we know that when this person threw this ball, it had a velocity of 10 meters per second. So imagine that if we were going to draw this as a graph, right? You guys graph quadratics in math class? Yeah. So if we graphed it, it would look something like this. This would represent, this axis represents time, right? So we could either be 4 seconds in the future or 6 seconds in the past. If we graphed this, it would look something like this, right? Where this is our 120 meters. And what we're saying here is that at this point, it's not quite to scale. That's better. If it already has some velocity and we draw this parabola, what we're saying is the point where he threw it, the ball would have already been on the way down if it had just been a horizontal throw that had a symmetric path. So we're saying it already had some velocity, so he was already closer to being to the ground. 6 seconds in the past is where that ball would have been if it was traveling along a parabola. I don't know. I think it's kind of interesting. We'll see more of that later. Part B says, how fast is the ball going at the moment of impact? So there, what we're trying to solve for is final velocity. So if we want to solve for final velocity, things that we know, our initial velocity is minus 10 meters per second. Our acceleration is minus 10 meters per second squared. Our displacement, our change in vertical position, is minus 120 meters. We know that the time is 4 seconds. That's handy. So which one do we like? When given the opportunity, I like to pick this top one because it's really simple and it's kind of harder to screw it up, right? If we start doing squares and things, it's easier to make mistakes. So final velocity is equal to my initial velocity plus acceleration times time. Our initial velocity was minus 10 meters per second. Our acceleration is minus 10 meters per second squared times 4 seconds. So we have minus 10 meters per second minus 40 meters per second equals minus 50 meters per second. So it's telling us that our final velocity is minus 50 meters per second, or 50 meters per second downward. Any questions? That was pretty straightforward. Number 6, last one, says when a kid drops a rock off the edge of a cliff, it takes 4 seconds to reach the ground below, which is interesting because it's the same amount of time it took this guy up here, right? When she throws the rock down and strikes the ground in 3 seconds, what initial speed did she give the rock? Okay, so we're going to need to solve some stuff because what we have here is 2 times. We know some other stuff. So if I've got my cliff, here's my kid. Kid drops a rock, right? If we drop the rock, that's right, drop. We know that our velocity here starts at 0 meters per second. We know that the acceleration is minus 10 meters per second squared, and we're told it takes 4 seconds. So for that situation, we know 3 things, so we can solve for the other one, right? We can solve for other stuff at least. If our kid throws the rock, we know that it has some velocity that's not equal to 0. So we know that that's true. We still know that the acceleration is minus 10 meters per second squared. We're told here that the time is 3 seconds. And then we're asked for our initial speed. But we can't solve that because we don't know another piece of this. So knowing the final velocity doesn't help us with the first problem, with the second part, because the conditions aren't the same. But the thing that is the same is how high the rock falls, or how much distance the rock covers. So if we can solve for our height, then that's going to help us. With acceleration, time, and initial velocity, we could use this middle equation to solve for that. So we can say that our displacement, our distance that the rock falls, is equal to the initial velocity times time plus 1/2 times the acceleration times time squared. So we've got an initial velocity of 0 meters per second times our 4 seconds. So that's going to end up being 0, and we don't need to worry about it. Plus 1/2 times 10 meters per second squared times our time squared, which is 4 seconds. So we're going to need to do 16 times minus 10 divided by 2. That tells us that our displacement is minus 80 meters. So that's how much it fell. We can take that information and put it into the other situation. 80 meters. And now we know acceleration, time, initial velocity. Sorry, we need to find initial velocity and we know our displacement. Yeah, so we're going to use our same equation again, but solve for something different. Oops. Only this time we're going to solve for initial velocity. So we've got minus 80 meters equals our initial velocity times 3 seconds. It's 1/2 times minus 10 meters per second squared times 3 seconds squared. Point 5 times minus 10 times 3 times 3. All right, so I can add 45 to both sides. So if I take minus 80 plus 45, I get 35. And then my initial velocity should be minus 11.7 meters per second. So downward with 11 meters per second. And this kind of makes sense. Because up here, it took 4 seconds for our object to get to the bottom. Oh, it's a different distance, so it's kind of doesn't really apply. How'd you guys do on that one? I like that we have consensus about the answers. Makes me feel like we all did them correctly. All right, what questions do you guys have about those? How do you feel about them? Seems okay? All right, so tomorrow we're going to have an online day. My plan will be that we work on worksheet number 2. What happens different with worksheet number 2 is we're going to start looking at solving problems that have a horizontal component. And so tomorrow you're going to start to see us using this one equation with horizontal motion. So we're just adding a little bit of a tweak to this. Okay, you guys have any questions for me? No questions? Okay.